Hello, ladies and gentlemen. Today we are going to take a look at some other proportionality theorems that come into play when we talk about similar. Some of them deal with triangles and then some of them do not today. So for this you need your notes, and I have also given you labels that go into your notes, so pay attention for that. Those actually have the theorems written on there. And then you're going to write a few examples after each label that you post. Okay, so you're going to post the label and then we're going to fill in, complete that part of your notes with an example. So you would want those labels handy as well as something to write with and a calculator. All right, let's take a look at the first label, ladies and gentlemen, that I need you to get into your notes. This first label deals with the triangle proportionality theorem. So this one still has to deal with triangles here. It says if a line parallel to one side of a triangle intersects the other two sides, then it divides the sides proportionally, okay? So notice in the triangle QSR here, this big triangle, we have two side, or we have the side that is actually the up and down side here, the vertical side, and a line that's going parallel inside the triangle. Check that out, okay? That line that's parallel to this side divides the other two sides proportionally. So that means if we were to compare this piece to this piece and this part to this part, we would have a proportion or two ratios that would be equal. So with that in mind, we're still talking about the triangle, right? But one triangle and not, in fact, two similar triangles, okay? So let's take a look at what that would look like in an example. After you've placed your notes there, okay, after you put that theorem in your notes, let's go ahead and draw this example. We have the situation that's happening here is that we do have a triangle and it has a line going parallel to a third side here. And when that happens, when we have two lines parallel to each other, and in this case you didn't know that because I hadn't drawn that in there, so I just did that part, you will know that this side and this side are split up proportionally. So that means if we were to make a ratio, we could compare this 8, the larger of the pieces on the left, with the smaller x piece on the left, just like the 24 piece on the right compares with the 12 piece on the left. Or I'm sorry, on the right. So if we go ahead and cross multiply here, you can see that we're going to take x times 24 is 24x, just like 8 times 12 is 96. And if we divide 96 divided by 24, you can use your calculator here or your good mental math skills. Some of you may have already seen this relationship. That x would have to be 4. Okay, and you can tell again because 24 is twice as much as 12, 8 would be twice as much as how much? That makes sense in this case, okay? So in this problem there was only an x, so you don't need to find x and y. Wrong directions there. All right, so let's go ahead and take a look at another theorem that we can get into your notes. This one is the converse of the triangle proportionality theorem. This is basically the reverse of what we just said. We just said that if you had basically a line running parallel to the third side, then you knew that the side lengths would be proportional. But here it says if a line divides two sides of a triangle proportionally, then you know it's parallel to the third side. So that means if you were given a way to check, like if this piece was 10 and this piece was 20 and this piece was 14 and this piece is 28, if you can see that same proportional relationship, oh, 20 is twice as much as 10, 28 is twice as much as 14, then you can conclude that these lines were in fact parallel. Okay, so this is just the reverse, saying you don't have to have parallel lines, you can check for parallel lines using those proportional lengths. So we don't need to actually write an example in for your notes. That's just something you'll check later on. This is the second label we need to get into your notes. This one's about parallel lines and proportions. So this one has nothing to do with triangles here. It says if three parallel lines intersect two transversals, then they divide the transversals proportionally. Not the parallel lines, but the transversals. So in this picture, notice that L and M are the actual transversals, and R, S, and T are the parallel lines. When this happens, when we have many parallel lines, 3 in this case, intersecting two transversals, we can conclude that pieces on the transversals are proportional. So for example, in their setup, you know that UW, this piece, compares with WY, this piece, just like VX will compare with XZ. So that's this little ratio you see down here. Now notice those lengths are on the transversal, not the parallel portion, okay? There's nothing in here about UV, WX, or YZ because those may not have a proportional relationship. All right, let's take a look at an example you should get down into your notes then. It says find the length from A to B, and in this little picture, I have basically placed an X on that portion. Okay, so when we see we have parallel lines, and we can see that because we have 90-degree corners here, ladies and gentlemen. That means those are all corresponding angles that are congruent. So we know, in fact, that these lines are parallel to each other. When we have three parallel lines, and what are two transversals, which we can see there, the one that's kind of diagonal and then the one that's going straight across horizontally, we can then say that we can find the lengths here using proportions. We know they're split proportionally. So let's compare, starting on the upper transversal here. Let's say that 16 piece would match with this X piece, just like, now we'd have to go back on the left-hand side here, the 15 matches up with the 18. So if we went ahead and cross-multiplied here, we'd have 15 times x is 15x. 16 times 18 is 288. And then if we go ahead and divide that by that 15 that we have in front of that x, we get x to be 19.2, or 19 and 1/5. This is completely fine. I know many times when we get those decimal values, we think we did something wrong, but not every ratio setup is going to come out to be beautiful integer numbers or whole number values in many of our cases in geometry, okay? So don't worry about getting those decimals. That's going to happen. So this is an example of when you have parallel lines. Let's take a look at the third theorem that happens to deal with proportionality. This is also back into our triangle, but it's an angle bisector theorem about proportions. So it says if a ray bisects an angle of a triangle, which means it cuts it in half, okay, then it divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides of the triangle. Okay, so this one's kind of strange, but in essence, we're looking for that ray to shoot through the middle of an angle. In this case, it's C. C is being bisected or cut in half. So when that happens, when that ray shoots through all the way through the triangle, remember rays don't end, then we can set up a ratio. Okay, that's equal to another ratio. So in this case, AD is matched up with DB. Notice that those are the two pieces that are matched up in the ratio. Those two are basically the segments that were created by that ray slicing through that side of the triangle, is comparable or in the same ratio as if I were to compare AC and CB, the original two sides of the triangle. Okay, so let's take a look at what that would look like in an example here. We're going to solve for x. This is the one you should write. This is supposed to be a D right here. Kind of got cut off a little bit. So you can see the original triangle ABC, and you can see that we have an angle bisector happening. Right here, there's an angle being bisected. And so this is the angle bisector that's cutting through that angle. And so when that happens, it splits that side, it's slicing through into something that we can make a ratio with. Okay, so if we were to start by making a ratio with these sides, A to C here, let's say that this x, who would that compare with? Well, it would compare with this other side over here, the AD side, which we would say would be 40 minus the x, because notice the whole side A to C is 40. The x piece is over here, so we'd say that this is 40 minus x, whatever length that ends up being. So this piece compares with this one. Now we need to go back on the right-hand side of our diagram and grab the 32, the whole side, comparing with the 24, the whole side. Okay, so we took each little segment made by the angle bisector and then compared it to the original two side lengths of the triangle. And now when we go ahead and cross multiply, we get x times 24 is 24x. Then we're going to take 40 times 32 now. 40 times 32 is 1,280. That's this piece. And we have to multiply it by the x, negative 32x. We want to get the x's together on one side, so I'm going to go ahead and add 32x here. And I end up with 1,280 is equal to 56x. So if I take that 1,280 and divide it by 56, we get x to be 22.9, or 8.5 if you want to round a little bit, or 8.6. Okay, so being careful now, we're going to go ahead and see that this piece is 22.9. And if we had to find this other piece, ladies and gentlemen, we would just subtract, like it says, 40 minus x. You could actually figure out what that calculation would be. So if I minus that from 40, I get around 17.1. Okay, 17.1 for that little piece right there. But in this example, all we needed to do was solve for x, okay? So let's put this all together now. One last example in your notes, everything that we've used so far, putting it together to determine the length of each segment. So the first segment we need to figure out says B to C. So I'm going to go ahead and place a little X right there on that measurement. And I'm noticing that I have parallel lines happening here. Interesting. Okay, so the parallel lines will split the sides proportionally. So I can set up a little ratio to solve for B to C. So for BC, I might say 5, this piece, matches up with this piece, just like 6 matches up with X. And then if I go ahead and cross multiply, I'd get 30 equals 5x, or x equals 6. So B to C is 6. Nice. Now let's find FC. Now notice FC is on the parallel line itself. Now be careful, in order to solve for that piece, we need to use similar triangles, because the theorems didn't say the parallel lines were split proportionally. They said the other two sides, the transversals, or the other two sides in the triangle, were split proportionally. So we need to use our similar triangles in this case. So we want to be careful that we see some similar triangles in this picture. Let's look at this big triangle here as one triangle. So let's say I was going to use this one as well as the big triangle that's in this picture, because I do see I have a 15 marked on a parallel side. So the littler red triangle for myself has a left-hand side of 10. Just like the big triangle all the way around has a left-hand side of 17. 5 plus 5 plus 7. Just like, now let's go, the bottom of my little red triangle is x, just like the bottom of my bigger red triangle is 15. And if we go ahead and cross multiply, I'd get 17x equals 150. So I take 150 divided by 17, and I'd end up with 8.8. Okay. Now, how would we find, let's say, G to B? This piece, if this was the x now. Well, similar idea, right? Now we're just going to use this little tiny triangle up here, but we have to use similar triangles because that is actually on a parallel side, okay? So we have to use the similar triangles. Let's use that one and maybe the big one again. So the left-hand side of the tiny red triangle is 5, just like the left-hand side of the really big triangle is 17. The bottom of the little red triangle is x, just like the bottom of the big triangle is 15. And we get 17x again equals 5 times 15. So if we go ahead and calculate that in a calculator here, just double check in 75, and then I divide by 17 again. Do not fear. Yep, you get 4.4. Okay? Nice. And now, last but not least, we're back to finding, I think I'm going to put a box around all these so we can find our answer later. We're going to go ahead and find C to D, which is this portion right here. And now that portion, ladies and gentlemen, you can call it X, Y, Z, whatever you want, but that is on a side that we can consider is divided proportionally. So we can do a little cross multiplying without looking for similar triangles. So we could maybe say that this 5 up here matches with the 7 way down below, just like the 6 way up here matches with the x way below. Okay, and then if we cross multiply, we get 42 equals 5x. 42 divided by 5 ends up being 8.4. Okay, so using all that we've done, similar triangles when we have to, this idea of dividing sides proportionally when we don't, we're going to be looking at different ways that we can set up these ratios to solve for missing pieces of diagrams, okay? So I want to thank you for taking good notes again today, ladies and gentlemen. Your notes are done, and I'll see you later. Thanks.